So now we're going to hone in on the relational model. We're going to talk about the relational model itself and what defines it, as opposed to, say, other models. But after we get through the terminology, we're actually going to dig a little bit deeper. We're going to explore schemas, which are the things that make up how we organize the data, whether we're looking at the organization of a particular relation or the organization of the entire database, which is a set of relations. And then we're going to talk about keys, which are a huge fundamental piece of how we define our relations. So this is, as I mentioned before, when we were talking about constraints, when we were talking about models in general, I mentioned that the keys, but more importantly, keys in general are constraints. We're not going to talk too much about the rest of the constraints. We will a little bit when we talk about the domain, but we're going to focus in particular today, at least, on key constraints, because they do make up what becomes our individual relations. So a relation itself, or the relational model itself, excuse me, is based on relations. Now, again, if you've read Ted Codd's paper, you'll see that this is the terminology that he used. You're probably, if you've worked with a database ever before in your life, you're probably more used to calling this same concept a table. But the two terms are really pretty much interchangeable at this point. I'll talk a little bit more about a table when we get into creating things with SQL, and we'll see that there's a little bit of nuance in the language, but conceptually, these two things are the same. It's a two-dimensional representation of the data. So, if you think of a spreadsheet, you have rows and columns, right? So our columns in this case are title, year, length, and genre, and our rows are the individual movies, Gone with the Wind, Star Wars, and Wayne's World. We're going to come back to this particular relation and a few more with it as we go through and discuss the different pieces of terminology and how we tie everything together. And these are the ones that are in the book as well. So if you've read through the book, this should hopefully help shed some light on the same exact thing that you were reading there. So we're going to discuss it using the same exact examples, and I do throw a few more things in throughout the slides, but you can also reference the book for all these. In fact, these screenshots of these tables are right out of them. So each row, each movie that we listed there represents, and that should be a movie, not a move. Sorry about that. I'll update that for the upload. So each row is, representative of data that represents one movie, right? So we have Gone with the Wind. It was released in 1939. Its length is 231 minutes, and its genre is drama, right? Star Wars was 1977. Its length was 124 minutes, and its genre was sci-fi. So each one of these rows represents a movie. On the other side, if we look at the columns, each column represents a property. And this is really no different from a property that you're used to using in a programming language, right? So if you have an object, you define it by its members or properties. Those terms are interchangeable for the most part and really are just specific based upon which programming language you're using. But these, analogize the same thing, right? So if we were to represent a movie as a object in a programming language, we would have an object called movie, and it would have properties of title, year, length, and genre. So far, you can kind of use that example to come across, and that will work really well. Let's look at some terminology now, because I'm going to still refer occasionally to, say, rows and columns, but really what I want to do is hone in on the terminology that is actually used for relational models. And we talked about a relation, right? And we said that's analogous with a table, and that is a data structure that consists of a heading and an unordered set of tuples. Now I'm going to get to what tuples are in a moment. They're down here, but those are the rows. So in our case, the tuples are the movie Gone with the Wind with all its supporting data there, Star Wars, and Wayne's World. And they all share the same type. Now, the type in this case is the relation, right? So Same, you can kind of think of that as when you're creating an object in an object-oriented programming language. That object that has those properties that we discussed, that object itself is a type, right? You can also obviously type those individual properties, but the entirety of the object itself is also a type. A domain. So the domain is basically, in a nutshell, the type, right? So it's the data type of an attribute. And you can think of this in the object-oriented programming land. If you have your movie and you have that title, right, your type would be string. And if you had the year, your type would probably be int, or it could be like a date or something like that, but they just had the actual year, so let's keep it simple and call it an int. You know, those are the data types, and here we're just going to refer to them as domains. And we do the same thing in a database that we do in a programming language by assigning a type to each of the attributes. Now, one important thing I want to point out is that in the relational model, we only use simple data types for attributes. This is a big difference from, say, like the NoSQL world sometimes. It is not uncommon for the NoSQL world to persist objects as values, right? Sometimes. So like if you have like a JSON representation of an object, and let's say it's a person, and inside that person you have a property of address. An address is a complex object, right? So that's actually another object in your data model that has, like, you know, my street address, my city, my zip code, etc. But that's all represented there as a property within my user object. So when you persist that through JSON, you can represent an object as the value of the name value pair as one of the properties of the parent object, which is a user. And if you persist that through, you can save it just like that. And this is one of the reasons when we get further on in the course, we're going to spend a lot of time, because this is what we do as programmers, learning how to map from our data model in memory to our database on disk or persistence, which obviously a piece of it can be in memory, but the translation there is important, right? So because the relational model only supports simple data types as attributes, that means that we have to oftentimes perform this mapping, right? Where if you don't have that constraint, you can have complex data types inside a complex data type and represent that, possibly, depending on how everything's set up, right out of the box, right? So when you persist something, say, in MongoDB, because it's in JSON and you have complex data types stored right inside of a complex data type, you just store it. You're done, right? So that's an important differentiation from the standard, NoSQL versus relational, right? So an attribute now, I've mentioned this a couple times. So an attribute is our column, right? This is a name paired with a domain, so a name and a type. So if you go back here and we look at our title we said was a string. So the combination of the name title and the fact that this column is a data type string, that makes an attribute, right? So an attribute of the relation is this particular column. And that is where we're obviously going to store our data, which I'm going to jump down, is called a component. So each one of those items, Gone with the Wind, Star Wars, and Wayne's World, ignoring the year, length, genre, all that, just in the title attribute, those particular data points are components. Now, going the other way, I'm going to jump back up. A tuple is a row, right? So that is an individual movie and all of its supporting information. So a tuple is Gone with the Wind, 1939, 231, and drama. That entire row represents a tuple. The same with Star Wars, 1977, 124, and sci-fi. So these, now you can take attribute, tuple, and component and kind of mentally insert into their attribute is a column, tuple is a row, component is the field or value at the intersection of that attribute and row. So here is a little bit of a graphic that kind of lays that out. I actually grabbed that graphic right off of Wikipedia, and it does a great job of showing exactly what it is. So you can think of the relation as the whole table, right? Remember, it's a two-dimensional, two-dimensional form to show our information. Our tuple is our row, our attribute is our column, and the intersection that we're looking at is our component, which is our field or value. All right, so let's look at a relation schema. So the term schema here is used in a bunch of levels of abstraction. So the first level I want to talk about is the relation itself. So the relation, remember, is analogous with our table, and the schema of our relation is defined as the set of its attributes. So having a title, a year, a length, and a genre gives us the schema of our relation for movie, right? So that is one layer of abstraction of how we can think about the word schema. The other is the actual relational database of schema. Now, I'm going to come back to this in a second. That's adding in the data types, but I'm just going to come back to that in a second. The database schema is now the set of those relational schemas that constitute the entire database. So that can be summed up in this slide, right? If you look here, we have our movie schema, and don't worry about the underlines and the data types yet. I'm going to come back to those. But we also now have other schemas as well for different relations. We have the movie star, we have stars in, we have a movie exec, and we have a studio. The combination of all these relations is the database schema. So the individual relations have a relation schema, and the combination of them is the database schema. In both senses, schema is the description of the definition of that thing, right? So in the relation schema, the definition is the set of attributes. In the database schema, the definition is the set of relations, right? So it's just a kind of hierarchical approach to the same term, right? Now, I wanted to come back to this. So we talked about the domain earlier, and we said that the attribute is actually the combination of the name and domain, right? So we also can represent our relational schema as that as well. So we don't have to just have the titles, right? We can also include, and probably should, generally speaking, unless we're just trying to write things out shorthand, the domain as well. So when we do that, we add a colon after the name, and then we put the data type. I've stuck with what the book had here with everything being lowercase, because remember that even though, like, if it's an object-oriented programmer especially, you probably are twitching looking at string, because string is not a primitive data type, right? String is an array of characters, and a character is a primitive data type, but a string is actually an object in almost every programming language. So that would normally be capitalized. But in this case, we're referring to a string as maybe like text varchar or something like that. We'll get more into individual data types that are specific to different database implementations later. But to us, a string is primitive, okay? In the context of relational databases, a string is actually primitive. So that's why we can do that, and it's just denoting that this is a string, which is basically an array of characters. What the implementation details don't really matter at this point. To us, it's primitive. It is not a complex data type. All right, so that is how we define our domain as in our relation, as we define our relation. We talked about our database schema. Let's look at this for a moment before we move on. So here is our database schema, which is a set of our actual relations. And we talked about the movie one, right? So don't worry about the underlines yet. We're going to get back to that. But we talked about the title, the year, the length, the genre. There's now actually some new ones here. So we have studio name, which is a string, and we have this weird one, producer C#. It has nothing to do with the programming language. This is a reference to the producer, who is a movie exec. So you'll see on the fourth relation down here is called movie exec, which has name, address, the cert number, which is an integer, and the net worth. That cert number is a unique number to identify a movie exec. We're going to talk more about keys in a moment. And the producer C number, it says C#, just I liked it because it's the capital C and the sharp, so it sticks. The producer's, it's really abbreviation of cert number, is a reference. What, for those of you who have touched this before, you would call it a foreign key, but we're not going to be on that terminology yet, to reference who the movie exec is, who made the movie, right? Our movie star has a name, an address, both strings, a gender, which this is a new domain we haven't seen before, which is just a plain character, just symbolizing to put one letter there, and it's probably going to be an M, an F, whatever. And a birth date, which is a date type. Now, the stars in relation is interesting because this is actually a combination of our movie, which we're going to talk about in a moment when we get to keys, but we're identifying our movie by a combination of the title and the year. And notice that we call it movie title and movie year because that's a reference to the fact that these fields reference the title and year fields that are in movie, right? And then also we have star name, which is a reference to the movie star, which is directly above relation, and it's a reference to the name component of that one. So, and that one's also a string. Movie exec we talked about. I didn't mention net worth really, but who cares? They're worth a lot of money, I'm sure. And the studio is the last relation here. This one has a name, which is a string, an address, which is a string, and then it also has a pres C, which, let's see, what is this a reference to? This is a reference to presentation C. I don't even know what that's a reference to. Well, I'll come back to it. I'm looking. There might be another table that's further down. I'm not going to worry about that yet. Oh, it's the president. That's what it is. So, okay, sorry. The producers, so like we had in movies, we had the producer cert number. The cert number really throws me off. It's not wouldn't be my first choice of a key name. But this is referring to the president of the studio cert number. So it's a reference back to that same movie exec relation, and particularly to the cert number component there. All right, so one more topic I want to touch on here as we're discussing schema. So we talked about the relation schema, right? We talked about the database schema. And now the last piece I want to talk about is an instance. An instance is a set of tuples for a given relation. Now, that might seem redundant at first, right? You're like, well, isn't that the same thing as the relation? And it's not, because now we're considering that the relation could change through time, right? We had an example here, where is it? Where we have 3 movies, right? But these weren't the only 3 movies ever made. So if at one point my database had these 3 movies in it, and now it has 5 movies in it, the instances have changed. There's been 2 instances at least of this relation, the one that had 3 and the one that had 5. So really what we're saying here is that we're going to add time in as a component. So this is important because we have to acknowledge, do we care about time any more than now, right? Because a standard database will only ever have the now version of the relation, right? If I alter one of these things, like if I go back here, sorry for flipping back and forth, and I change for some reason the length of Star Wars. Say it really is 124 minutes. It was 126. I mistyped it for some reason. Unless I have some way of capturing that historical information, it will not be retained, right? So if I change this, if I change this yesterday, it could have existed with the 124 for years, prior, since 1977. Who knows? And you would have no idea if you looked at it today, right? There'd be no record of that because standard, there's no relation, does not give you the ability to record history unless you do something special. Now, databases that do maintain historical versions, they're referred to as temporal databases. Now, one thing that we'll be using this semester for the second half of this is a library that I created that's an object relational mapping library, and this is what we'll actually be working with and learning how these things work and how to actually map from an application space and objects in memory to database space and objects that are going to persist and break down into relations with absolutely simple attributes, right? So that one of the properties of that object relational mapping tool that I created is that it makes every database that you create with it inherently temporal. It will remember history on everything. And you don't have to lift a finger to do it. The infrastructure of it does it itself. It adds 7 fields to every database table that it manages that know what time that row was updated, what time, what time there's like a start and an end time. So like, if in our example you updated the Star Wars row, right, it would take the original row and it would give it an end date, of like yesterday, whenever you changed it, and then there'd be a new row that would exist, and that would have a start date at the same time of the previous one's end date, and then it would have no end date if that's the current row, right, for that second row. So there's a lot more to it than that, and then there's this whole service layer where, as a programmer, it will wrap that all up for you in a bow and give you back this one object that contains both the current information and all the historical information. So there's a lot of plumbing that goes into that at the application level, but that is one of the things that it does. So we'll be playing with that later in the semester. This is going to be something that we're moving towards, right? And it's an important thing to discuss. I mean, because it's just an honest fact that the vast majority of data stored in relational databases is not temporal. It's not even close to being anything significant. There are usually what are called history tables that are maintained for really special data that, it would be absolutely detrimental to the company or enterprise or whatever if this historical information was not maintained. So usually those pieces that are required are identified, and then a special thing is set aside to make a solution for that. But generally speaking, solutions that actually make all of the data temporal are rare, and we'll talk more about why. I mean, most of it's the complexity, but it's also the amount of data that you have to store may go up even exponentially depending on how much your data changes. And sometimes you just don't care, right? There's some data that you're just like, I really don't care if I have anything other than the now version. The now version is all I want, right? So these are all reasons why, that's a discussion. So schemas, wrapping up with schemas, we have the relation schema, which remember is the definition. It's the set of attributes. And we said the attributes are a combination of the name and the domain. So you take each attribute, which is the name and domain, and the set of those attributes makes your relation, and that's your relation schema. Now, if we take all of those relations, the set of those relations is your database schema. And now we've said that an instance is a schema in time, right? So an instance is that relation, or you can look at it as the whole database as well. There's no reason why you can't. Obviously, changing one of the relations, alters that relation, and it's a different instance of that relation than from when you altered it. But it also alters the entire database, right? So both your relation and your database schema are, contingent on a particular instance in time, and they represent that instance. All right. Now, the last topic here that I want to discuss, and it's an important one, is how we define a unique tuple, right? So we have our relation, and we know that the rows in it we're referring to are tuples. We have had our examples of the movies with Star Wars and that kind of thing, and we know that there was Gone with the Wind and Star Wars, and they were all separate tuples. But what makes them unique? We need something called a key, and the key of a relation is a set of attributes such that no pair of tuples has the same key. So in other words, we can't go back here, all the way back here, and have two different tuples that have a title of Gone with the Wind, a year of 1939, a length of 231, and a genre of drama. Now we're going to actually whittle that down even more so that you can't have all four. We're going to actually whittle it down to two, because that's what the author did. I don't know if I agree with it, but it wouldn't be my choice as a database designer, but that's the beauty of the discussion. But before we even whittle it down to two of these things, you can say, just at looking at all of the attributes, that you cannot have two rows that have an absolute duplication of all attributes, because they're the same thing, right? We need to make sure that they are unique. So that is what we're doing here. We're defining what makes them unique. So you can have, what you want to do is you want to have a key, and the key can consist of one or more columns, and if it's more than one column, we refer to it as a composite key, but that's not too important right now. And these have to be unique. So let's look at movie, right? For movie, we're going to say, sure, let's do movie, and we're going to go with what the book did. Again, this isn't my first choice. We're going to use title and year. So the book has some discussion on this, and they go back and forth. They basically say, I don't know much about movies, but they basically say, at least in their opinion, that you can't have two movies with the same title in the same year. You might have two movies with the same title in different years, but you shouldn't have two movies with the same title in the same year. So the combination of the movie title and the movie year makes that unique. So you could have Star Wars in 1977, and you could have Star Wars in 1979 or 80 or whenever the next one came out, but you can't have two Star Wars in the same year. And yes, I know that they weren't both called Star Wars, but that I was just using as an example. The Empire Strikes Back is obviously not the same movie title, but there are movies where sequels use the same title, and I guess it's taboo to use the same movie title for an unrelated movie. I don't know, but it strikes me as odd that no two movies have ever had the same title. But at any rate, wouldn't be my first choice, but that's what they're using, right? So that is the key for that relation, is the combination of title and year. So, or name, I guess it was, in year. Now, other examples might include like something unique, like a social security number. In that case, you only need the one column. Now, we'll come back to discussion on whether or not that's a good idea. A third example here, this again is a one column situation, and it's very common, is that you have something like a user ID or an employee ID. So we're here at Marist, and you guys all have a CWID, which is your college-wide ID. And the purpose of that ID number is actually so the college has a ID number that it can identify you by and all your records, but it's not necessarily something like your social security number that's private. So if it's posted somewhere, it doesn't affect you negatively for like identity theft purposes. It's just meaningful in the context of Marist College, right? So those are all good candidates for keys. Let's look like some others and see, what's good and what's bad here. So what I have here is these 6 examples. Before the colon is like a type, so a relation. So imagine that we're creating like a user relation for the first 3, and then the second 3 I'm going to use enrollment. So enrollment, of course, is a student who's actually taking a class. So you guys are all enrolled in database management systems, MSCS 542. So you are all an enrollment record somewhere in a database. All right, so let's go with the user one first. So the first one is a composite key, and the proposal is first name and last name. So is this a good composite key? And I would definitely say no. And I hope you were thinking no immediately as well. I've definitely had students, I don't know if they've ever had same exact first and last name in the class, but there is absolutely no reason why it can't happen. And I definitely have students with same last name. I just, in fact, had a class last semester where I had 2 last names with 2 students. So one was Smith, the other I forgot, but I definitely remember it happening because you go through the roster in the beginning of the year, you're calling attendance, whatnot, you notice. Now, I don't think I've ever, again, had a student with both first and last name be the same, but there's absolutely no reason why this can't happen. So this is a horrible idea. You should never, ever, ever do that. All right, second one is a user ID. This is a good one, right? So we're going to come back to, in a moment, if this is a made-up ID versus an already existing ID, like a social security number, which is the next one. But we're going to come back to that in a moment. But yes, an ID of any sort is a good one. Now, social security number, same idea. Yes, completely valid ID because it's unique. You should never, hopefully, have 2 people with the same social security number or the government screwed up, which obviously isn't out of the realm of possibility. But if it's valid, which it is it a good key, right? So I would propose no. I would say unless you are the federal government, I would not be using this as my primary key. Is it unique? Yes, but it's information that is considered somewhat confidential. I mean, granted, it's not like quite as bad as like a credit card number or something like that, but it's up there. It's one of the major things that, would contribute to identity theft and all kinds of problems. So I would not be using this as a key. Now, what's important to note is that you will oftentimes have relations that have multiple possible candidates for keys, right? You could say, for example, just in a user table, have a user ID, a social security number, and an email address. Believe it or not, any one of those 3 could be unique, right? So we're going to discuss what it's, the difference as far as like which one you actually choose to use. But the important part here, the exercise we're doing, is just identifying what is a valid key. Any one of the 3 of those is valid, but which is a good one? I would conject that we should use user ID out of these 3. All right, so now the next one. So this is enrollment. This is a little bit trickier. So enrollment is, remember, the combination of a student enrolled in a class. So a section is a class that is being offered currently, and it's basically takes into account the class's information. So usually there'd be a table or a relation called class that would say, for this class it would be database management systems, MSCS 542. It would have the course description. It would have that it's 3 credits, that kind of thing. The stuff that does not change every time this class is offered. Now, when we do offer the class, that's referred to as a section. The section is the combination that I am teaching it. It is given online. It is given in the spring semester. It is, whatever those things are, right? And those combination of factors now, that is the section, all right? So you enroll in the section. You don't actually enroll in the course in this relational model. You enroll in the section, right? So The first one here is the combination of your student ID, let's call it your CWID, and the section ID, what some distinct number that we give to the section. Is the combination of these two things enough? And intuitively, at first, it could be. I'm gonna say it could be. It's probably not, but I'll explain why. It's probably not, because usually you can enroll in more than one type. You can add a class, you can drop a class, you can probably add it online versus, adding it at the registrar's office or something like that. So that's referred to as an enrollment type. So I included this example here because it's a little bit more nuanced, but it's good at digging into what this problem is when you're designing a relational database, right? You have to really identify the true combination of attributes that gives you a distinct tuple, right? That's absolutely imperative. And odds are you're going to need that enrollment type as well. It is possible, of course, that there is no such thing as an enrollment type. All you can ever do is add a course. You can never leave it or something like that, and then that's fine. Those two would work. But more than likely, that's not the case. So you actually need the second enrollment example here, which is the section ID, student ID, and enrollment type all together. So it would be, the section ID would be this course, and its section, the student ID would be you, and the enrollment type would be add, right? That would constitute a row. If you dropped, then you would have a second row with the same section ID, the same student ID, but a different enrollment type, right? So now I have a record of you adding and dropping this section. All right, the last one here is also a completely valid option. So I could have an enrollment ID that I construe to represent a unique role, and this is very, very common in relational modeling. And what I want you to keep in mind, though, is if I do this, I'm more than likely going to have still those fields up there: section ID, student ID, and enrollment type, right? So this is now a made-up field that I'm adding to the mix. And that actually brings us right around to here, which is a perfect transition, because I said earlier that relations can have multiple keys, right? So we use the example of the user table having many candidate keys. It could have, an email address, social security number, a user ID, etc. So which one you pick once you select it is called a primary key. All right, so the primary key is what we use to separate our tuples. Now, once we've identified that, what we choose, whether it's like we just discussed, an unused numeric field. Now, what I mean by that is so if you go back here, enrollment ID is unused. It had no purpose, right? It is not representing the section ID you're enrolling. It is not representing the student ID, and it's not representing the type. All three of those things are concrete attributes that have purpose, right? They are data points that matter. The enrollment ID is something I just completely made up. It has no other purpose other than to be a primary key. And that's okay, right? So that's one of the things that we decide when we do the design of this. And it is very, very, very common for people to create these unused numeric fields. Oftentimes there'll be these auto-incrementing fields that when you do an insert or something, you don't even provide the number. The database automatically puts the row in and puts that ID field up to the next number. And this guarantees us uniqueness, right? Because this field has no other purpose. Its only purpose in life is to provide unique rows. It gives us a lot more flexibility, especially if you want to do something temporal now with history, right? I need more, right? I need things like we were discussing before about, start times and end times for when this tuple was the valid one, so I know. But if I have something like these IDs, these row IDs, let's call them, these unused numeric fields, then I can have as many rows as I want that represent the same basic data going back and forth. Maybe for example, my user record My first name was Brian, my last name was Gormanley. Somebody updated my record by accident, and they messed up the spelling of my name. They added an E to the end or something. And then they realize they messed up and they change it back. Well, if I have a historical database here, and granted there'll be hopefully some fields retaining the dates, but leave those out for a moment. My first tuple had my name spelled correctly. My second tuple had it spelled incorrectly. And my third tuple, it went back to being spelled correctly, right? So hypothetically, without any other discussion about like maintaining the date stamps that these things happened in, if I was maintaining that historical data, those two rows, the first and third, could be the same, right? So that having that separate unused numeric ID guarantees us a unique row. It guarantees us a primary key that is distinct, right? So there's all kinds of good reasons why we use kind of unused numeric fields for primary keys. It also makes it a lot easier to reference the thing. So we're going to go back to here for a second because I want to point this out. So the stars in, right? The stars in here has movie title, movie year. Now, we just discussed those two things in combination are the primary key of movies, which, by the way, is why they're underlined now that we've talked about that. But if we had an ID, if we had a movie ID, that was that unused number area that we could just have a number going up, then our stars in could be a little bit simpler. We could have just had movie ID, right? We wouldn't need to include both of those fields. So anytime you have a compound key, when you want to create a relation between these two things, you have to actually use that compound key across, right? So that makes that more complicated. And here's how we indicate our keys, which is what we just saw. So now we're taking where we left off with how we describe our relation, and we're just underlining the combination of attributes here that are in fact our primary key. All right, so I kind of went this way to get here instead of going back, and we just kind of talked through all this, right? I think the big one was the stars in. Like I said, that one kind of draws, from both movies and also from the movie star table. As we said, the movie exec table is used in both movies, in the producer C, and also in studio, in the president C. So those are also relations there. We're going to come back and spend a lot more time with that in the future, but for this week, that's what you need to know.